Bismillahirrahmanirrahim. Today we will be discussing Unit 3 of your IGCSE 0478 Cambridge course. And the topic for Unit 3 is actually a very lengthy topic, and it covers a lot of different pieces of hardware. But our focus for today will be the processor fundamentals and our von Neumann architecture and how it works and what different aspects are need to be discussed regarding the von Neumann, the different parts, subparts of the von Neumann architecture. So without further ado, let's begin. Okay, Ji. So we'll be focusing on this part first. We'll be discussing the central processing unit, the basic components such as the ALU and control unit, the different buses, what are the purpose of the core, cache, and internal clock with respect to the overall performance of the computer. What is the purpose of the fetch, decode, execute cycle, how it works, and eventually we'll be progressing towards understanding the instruction set and how a CPU is basically capable of identifying the difference between an instruction or an opcode and an operand, and what is the importance of a embedded system, how are embedded systems being used. Okay, so let's look at the central processing unit. The central processing unit, CPU, also known as a microprocessor or processor, is central to all modern computer systems, including tablets, smartphones, and even household devices today are come equipped with central processing systems. The CPU is very often installed and as an integrated circuit in a single chip. And what we understand about integrated circuit from the previous chapter is that it relies on synchronous parallel data transmission. So basically all of the cabling or the communication channels within an integrated circuit, including the communication with the CPU, are handled through a parallel synchronous channel. The CPU has the responsibility for the execution or processing of all instructions and data in a computer application. So basic major components of the CPU include the control unit. We'll be looking into the detail of how control unit, what it does, the basic responsibilities of the arithmetic and logic unit, and then we'll understand the different registers and the different buses. Okay, so before we move on forward, we have to understand how computing was before this person, John von Neumann, proposed the von Neumann architecture. So basically, as we understand the working of a computer is a sequential machine. So basically, it's carrying out instructions in sequence. So as I have mentioned a little while ago, we'll be looking at this in much detail as well. But basically, an instruction is made up of two parts. There is the opcode and the operand. The opcode defines what is to be done, and the operand defines what data is to be used for that particular instruction. So before the von Neumann architecture came into being, it was seen that the norm of conducting computing was that instructions were handled by separating the opcode and the operand, and they were fed to the computer system separately through punched cards or something like that. So there were different methods of providing data and opcode separately for a particular instruction to be executed. Now, obviously, because of this, uh, human involvement was very significant, and of course, uh, at the rate of how humans work, this resulted in overall very slow processing. Now, von Neumann proposed that since there is really no difference in visibly and storage point of view, there's all ones and zeros between an opcode and operand. Why can't we just store them in a single place instead of having you to give them separately for instruction to be executed? And if they're stored together in a single storage device, a CPU can be programmed in such a way that it can automatically fetch those instructions and execute them as their sequence. So as this was the proposal of von Neumann. Before von Neumann, as I mentioned before, that we were basically executing instructions by feeding the opcode and the operand separately, and that too when it's needed. So when I feed the opcode first, then when the operand is needed, then the operand is fed. So that takes a long time. Now, since all data is ones and zeros, may it be an operand or an opcode, I could put them both pieces of information in a common storage, and they can be held together. And the computer can access this common storage uh, by turn, accessing all instructions and executing them on its own without human involvement. So this was the fundamental motivation behind introducing the von Neumann architecture. Now, it has become the what you call it, the basis of all processes that we use today. Of course, over the years we have, and this is by the way in the 1940s. Von Neumann introduced this von Neumann architecture in the 1940s. So 1940s till now, we are basically using the same principle. Yes, over the time we have developed processes that are faster. They are, you know, there are multiple processes that are working together, multiple, with through multiple channels. And we also have larger packing storage devices, larger immediate access stores, larger RAMs, caches. But the fundamental principle of a computer operation remains the same since von Neumann introduced it. Okay, now basic features of a von Neumann architecture are as the CPU can access the memory directly. So by memory, we're talking, usually we refer memory, we link memory to a random access memory. And that's why random access RAM, ROM, and cache are referred to as the primary memory, because the CPU accesses them directly. And that's what is exactly means over here as well. Computer memories can store programs as well as data, and in the same location possibly, and they're all stored in ones and zeros. That's okay. And the location that has program and data at this moment may have something else at a different moment, because the situation of a primary memory is that is volatile. It's never permanent. It's constantly changing its state of data. So if I'm looking at a particular location, which is by the way known as an address, if I'm looking at an address and it has some data in it, after some cycles, that same address may have something else in it. So that's the situation of a random access memory. After that, stored programs are made up of instructions which could be executed in sequential order. And that this is the fundamental way of how a computer works. All the instructions that it executes to meet our needs have to be carried out in sequence. And who decides the sequence? Of course, we do. So whenever we write a program, we have to keep in mind that a CPU or the computer will execute this program or these set of instructions in a sequence. And we have to make sure that the sequence that we have written here is in line with our goal that we're trying to achieve from that particular program. So this is another concept we'll be looking at further more on this topic in paper 2, when we will be looking at the different aspects of a programming algorithm, or the different structures, basic constructs of a programming algorithm. And one of those is known as a sequence. So sequence we decide, because we are better judges of what we are expecting as an outcome. So based on that sequence, the computer will execute each and every instruction in that exact same sequence down to perfection. So if the computer is doing some steps wrong, it's obviously because you have programmed those steps wrong. The computer does not make any decisions on its own. All it does is carry out instructions that you have given to it in the form of a software. Now, as you can see in this diagram, this is the basic outlay of our computer architecture, or the processor architecture. The dotted lines represent the limitations of my CPU. So any device that you see here is confined within my CPU, this part of the CPU. Apart from this, we have every other device is not necessarily part of the CPU. Now, von Neumann, this is the earliest versions of what von Neumann architecture would have been. Now we see that our memory storage devices, such as the cache, are actually part of the CPU. So in that case, if you look at that, that cache would be here somewhere. But again, we are still focusing on the fundamental parts of the von Neumann architecture, and that's what these are. So as you can see here, I've got an array of registers highlighted by the yellow boxes. We got the memory address register, program counter, memory data register, current instruction register, and accumulator register. We'll be looking at these registers in a bit. Apart from that, we got other units such as the system clock, control unit, arithmetic, and logic. All of these components are connected with the outside world, anything outside of the CPU, with what are known as these buses. So we got the control bus, address bus, and data bus. Collectively, we can refer to these three buses as the system bus. So If my CPU is communicating with devices outside of the CPU, outside of this area, it is thanks to this system bus. Okay, now let's look at the different aspects of our different parts of our arithmetic logic, our one-to-one architecture, starting off with the arithmetic and logic. Okay, as you can be seen here, the the name itself states what this unit is supposed to do. So it's saying arithmetic and logic unit. So by that logic, it's supposed to be any time I need to carry out some sort of arithmetic operation, which is addition, subtraction, and arithmetic logical shifting. We have studied this in chapter 1. Anytime I have to carry out any such arithmetic operation, the arithmetic unit is helping me with that. Secondly, if there's some logical operations such as AND, OR, XOR, stuff like that, my processor's logical unit is carrying out those operations. So combined definition basically means that all arithmetic and logical operations are carried out by this. So as mentioned before, I've discussed this in paper 1, chapter 1 as well. Addition, basic operation is mostly just carried out through addition. So all operations are handled through addition. So if we addition is addition, subtraction is basically the addition of a positive negative number, and similarly multiplication is repeated addition. So if I have 3 multiplied by 2, I just add 3 plus 3, and that results in 3 multiplied by 2. Similarly, if I get division, that is repeated subtraction, which comes down back to addition. So practically all of the operations are just by handled by addition. However, if there are other operations that they require division by 2, 4, or 8, those can be handled much quicker through logical shifting. So if I'm dividing something by say 3, then I can't handle it by logical shift. Or if I'm multiplying something by 3, then logical shifting will not help me there, because 3 is the number that is not justified by the logical shifting process. However, if I'm multiplying something by 2, 4, 8, 16, then in that case, logical shifts can be used to shift the bit sequence around to form a new larger number. So if I have to multiply something by 2, 4, 8, 16, then I have a first faster method, which is known as logical shifting, either right or left to carry out either division or multiplication. However, if I'm doing any other multiplication division with any other number apart from 2, 4, 8, and 16, then I'll have to use the method I just discussed before, used through addition. Now let's look at what control unit does. The control unit reads an instruction from memory using the fetch, decode, and execute cycle. We'll be looking at this in a bit. During the process, signals are generated along the control bus to tell the other components what to do, of the computer what to do. So basically, when I say other components, what I mean is that everything. CPU is connected with everything. Now we are familiar with the term as primary memory, and we often think that just since primary memory is defined as the memory device with the CPU directly access, we always end up thinking that maybe the CPU only has direct access to the primary memory and nothing else. Now that's not true. The CPU has access to all parts of the computer. However, all parts of the computer are divided into two broad categories. One is known as the memory, and the other are the I/O devices. So excuse me. So if I have, say, for example, my memory, RAM, cache, they have to fall in the category of my memory devices. However, if I have, say, for example, hard disk and graphics card, keyboard, whatever, stuff like that, all of these things are, considered as I/O devices. So collectively, all of my devices are handled or controlled or linked with the CPU in one way or the other. So if I am carrying out instructions, what that actually means, if or my CPU is actually executing instructions, what that really means is that the CPU is sending out signals to all parts of the computer to make sure that instruction is actually carried out, or the physical effect of that instruction is actually implemented. So how that's happening is because the control unit is sending out these control signals. And since my control bus, which is linking my control unit to my all parts of the computer, may they be the primary memory or the I/O devices. Since the control bus is there, I'm using my control signals. I'm using my control unit to send out control signals to all parts of the computer to make sure that instruction is carried out as expected. Then we have the system clock. A system clock is used to produce timing signals on the control bus to ensure that vital synchronization takes place. Without the clock, computer would simply crash. Now, one example of this synchronization that we're talking about here is that my CPU may have to switch between different processes. The only way the CPU is capable of carrying out so many processes simultaneously is through this process of known as context switching. So by context switching, we mean that the CPU is executing one instruction for some cycles, 8 cycles or 4 cycles, and then what those 4 cycles end, that instruction is stopped, the state of that instruction is saved, and that instruction is sent back to the memory to wait for its turn again if it needs the CPU more. And when the CPU allocates time to another process, it's the same thing. It gives it the fixed time, which is also known as the time slice, and make sure that those instructions, those processes are only executed for that duration of the time slice. Once that time slice finishes, that process is halted. The state of that process is saved because I want to continue from where I left off, and that process is sent back to the ready queue, where or the waiting state, or the memory, where it will wait for its turn again to be given to the processor. Okay, but if I don't have a system clock, these synchronization activities, amongst other things, this is one example, these synchronization activities cannot take place. And if I cannot handle synchronization inside a computer, my computer will simply stop working, which is known as system crash. Now let's look at the purpose of the immediate access store. Now I have mentioned this before, but the immediate access store is actually another name for our primary memory. Now this primary memory is basically the device that the CPU directly accesses. Now this could be either the cache, ROM, or the RAM. But now since we're talking about execution of programs while the computer is running, we'll be focusing on the RAM and the cache. Now cache and RAM are both types of, basically RAM, but the cache operates faster than the RAM, it's more expensive than the RAM, and obviously is smaller than the RAM. So if I, for example, have a program that's running or a process that's running, the frequently used instructions will be part of the cache. So the part of the program, the whole program that is running is known as a process, and that resides in my main memory. And the part of the process of the few instructions that I frequently need right now are made part of my cache. And this way, my CPU has access to the cache as faster device, smaller device, closer device to access the frequently used instructions, thereby making the overall processing of your computer faster. So then we have a term known as the backing store. Now, backing store is a permanent storage device, as unlike IAS, which was a temporary storage device, volatile device, the backing storage is a permanent storage device. And by permanent, we mean that it is the device that is commonly known as the hard disk. All programs that are saved, all programs and their data are permanently saved in the hard disk. So that means the data will reside there until you delete it, or if, say, for example, some physical damage or some virus or some malicious intent hits the hard disk. So otherwise, there's no way of automatically deleting it. So now coming back to the terms again, just a quick recap. The IA immediate access store is another name given to our main memory, and the backing store is another name given to our hard disk. The main memory will have the process that is running right now, and the program will the hard disk will have the whole program that will maybe needed in the future. So let's just say I'm running a process in my main memory, and I need another process for the same program. I'm playing a game, for example. So I'm playing a game, and I'm at level 3, for example. The level 3 process is running, and I'm playing the game. I'm moving around. Now level 3 process is finished, and I start level 4. Now level 4 screen loading starts. So that loading message shows up, and it takes a long time. What's happening during that loading session is that basically the level 4 instructions are inside my hard disk right now, and I'm basically breaking them into my main memory. And the time that it takes that I'm wasting from breaking something from the hard disk, which is very slow device compared to the memory, it's known as the loading wait, loading delay. And that's how you are present. That's why you presented a screen on your loading screen That basically means that your program is being brought in from your hard disk into your main memory. Okay, now let's look at what the registers are, what different registers. We in the previous screen, we saw that our CPU is made up of the control unit, system clock, arithmetic logic unit, and a variety of registers. Now let's look at these registers. Okay, the first register we see here is known as the current instruction register. Again, the concept here also makes sense that we are looking at the name and just identifying, just by looking at the name, we're capable of identifying what this register actually does. So in this case, the current instruction register holds the instruction, holds the instruction that is about to be executed now by the control unit. So right before the instruction is sent, the opcode part of the instruction is sent to the control unit. It is held in the current instruction register. So apart from the accumulator register, the current instruction register, memory address register, memory data register, and the program counter, they are known as specific purpose registers. Now, by specific purpose register or special purpose register, we mean that the contents of these registers are of a certain type and they always have a certain meaning. So now, like we just saw, the current instruction register is a very special purpose register. The contents of this register will always be an instruction. And the meaning of the contents of this register is that this instruction will be executed now. Then it's now turned to execute this instruction. So this very specific purpose of this register. Same thing goes with the MAR. Memory address register has a very special type of content, which is the address. Address of what? The location, the place in the main memory from where I'm either gonna read data or from where I am gonna either write data. So wherever I'm gonna access the information right now, I need the address. So that address will be held in the MEF. So again, special purpose in the sense that it has a very, distinct purpose that it holds the address of where data is either going to be written to or where it's going to be read from. And secondly, the contents are also specified. Its contents will always and always remain an address. Same thing goes with the MDR. MDR is memory data register, also known as the memory buffer register. Now again, the purpose of this register is that it holds the data that has just been read or the data that is about to be written to in the memory. So very special purpose, very down to, very down to the last detail purpose, very specified purpose. Secondly, the contents of the MDR are also very specified. They are not an address, or at least they're not only an address. They can be an address, but they're not only an address. MAR only has addresses. MDR's contents is data. Now, by data, we can say that it's some information, some data, it's some value, it's some number, or it could also be some address. So when we have collectively, it could be anything, we call it data. However, if I'm specifying something, it's MAR. It only has MAR. Let's come to the PC. PC stands for program counter. So like we discussed before, our CPU carries out all instructions in a sequence. So basically starts off with the first address, picks up the first instruction, executes it, moves on to the second address, picks up that instruction, executes it, so on and so forth. Now, how did my computer move from address 1 to address 2? Who told it? Well, that's the responsibility of my program counter. Program counter simply points to the next address from where you are going to be reading data or reading an instruction and executing. So every time you read an address from my PC, it increments and starts pointing to the next instruction, so that when the fetch execute cycle is ended and you come back to the PC, you will know beforehand which address to access to for the next data. Okay, so these were the special purpose. Now let's look at the ACC. The ACC can hold anything. It could have an address in it. It could have some value in it. It could have some binary, logical operations and the result of a logical operation in it. It could be anything. But it is a register that is used when carrying out arithmetic and logic unit. So whenever you're doing some addition, and we'll be discussing this, in fact, not we, but A levels does this in three different, three or four different instances throughout the A levels clear. And this is known as assembly language. And when we study in assembly language, we will see that everything ends up in the accumulator register. And the contents of the accumulator register are used for further processing. So if I want to add something, say for example, I will say add. Let me give you an example right here. Let's just say I'm writing an instruction in assembly language, and I wrote something like LDD 40. Now, what this means is that I am loading. LDD is a mnemonic, by the way. Mnemonics are used in assembly languages. These are three-letter words, at most three letters, and they have a very. This is basically the opcode. So if this is one instruction, this is the opcode. What do I want to do? And what is the data I'm using? That's the operand. So LDD is this opcode, and it means that I want to load using direct addressing. Now, load using direct addressing means that whatever the contents of this address are, I want to bring them into my CPU. So assuming that 400 is an address, its contents, say for example, its contents are 50. So now 50, the value 50 will have been accessed, and 50 will be used, will be brought into my CPU. Now, when I say brought into the CPU, where exactly? The accumulator register. So LDD40 means it brings the contents of address 40 to the ACC. Now, following this instruction, this is very interesting. Let's just say I will I'll write the next instruction. The next instruction goes something like this: add hash 30. Now, what these hash, you're not supposed to memorize these things, but I'm just giving you an idea of how the accumulator register works. Now, add hash 30 means that hash when I add hash to something, then it means this operand is not an address, it's the actual value. So if I don't add hash, it means this thing is an address. This hash means that this is not an address, this is the actual value. Now, what add hash 30 means that it adds the value 30 where? In the contents of the ACC. So it's always the ACC. So add hash 30 does what? It adds the value 30 to the contents of ACC, which is, by the way, 40. And where does the result go? Back in the ACC. So now my ACC has the value 70 in it. After that, I can go around and do this, store 60. And what that does is that it stores the contents of ACC, which is 60, to the location pointed out, or the address 60, like this. So very interesting language, very, it's kind of difficult to use. It's not, if you are familiar with high-level programming languages, this looks very different, but it has its own benefits, in own applications. Very interesting nonetheless. So this is the basic purpose of your program counter as well, that it basically carries out instructions, first of all, in sequence, and make sure that all data is handled in such a way that all instructions are carried on sequence, right? Now, what is it? And then finally, let's look at the ACC. As mentioned just a while ago, the ACC holds the data that is required in arithmetic operations. So we just saw that when we added something, the result was stored back, we added something with the contents of the ACC, and addition is an arithmetic logic operation. And the result of that addition is stored back in the ACC as well.